That's
So you
true.
can see my screen?
Yep,
Are you
alkyl groups, alkanes.
Okay,
Alkyl
are you recording?
Yes, we're recording. So let me
Good.
just announce, I'm Salvador Cordova, and here are my two friends, SpeedOfSound and Immutable Destiny. And they're going to school me on basic science and organic chemistry. They're very generous to spend time with me as I'm trying to learn this topic. So Mike and Immutable, take it away. And then I also have some of my homework things that I could share with you. And you could look at it.
Basically, from the last time, what I wanted to go over is the very important alkanes and the alkyl groups, which right here, basically we have on the, let me get some red. Right
Methane
here, right,
at the top.
methane, yep, methane or whatever, and then
Methane,
ethane,
methane, propane. I don't know what the 4 is. Then pentane.
butter. Remember butter? Butane.
Oh, the butyric acid. Oh my goodness.
Butyric acid, butter. So what just happened? Why is this doing this to me? And then pentane. So
what is number 4?
Number 4 is butane.
Butane.
Yep. So they're unfortunately named alkyl groups, alkyl, with the Y here. And so this would be a methyl group, an ethyl group, a propyl group. If it's attached to something else, that's basically how you would name it. And a butyl group and a pentyl group. So they can also be groups. I mean, they can be standalone molecules or they can be groups. And then, go ahead.
So I had a question. So we call these single bonded carbons with hydrogens or carbons with carbons as alkanes.
Alkanes, yes.
We call the group the alkyl group. Is that correct?
Yeah, it's an alkyl group.
Okay.
And it's unfortunate that they use the Y.
Because it's like alkene kind.
Alkenes have double bonds and alkynes have triple bonds.
So actually, this is good to know because this isn't exactly what the book says. I'll go by what you say.
Yeah, let me know what the book says because the book is probably right. My stuff is like 40, 50 years old. There are several different ways to name things. There's the standard way to name things, and then there's
IUPAC nomenclature.
Yeah, yep. And
the IUPAC nomenclature is really it's a system that only a mother could love, but it has to exist.
Right, because it's very specific. So it
all
fits
right.
in. The nice thing about the Wikipedia is if you look up any compound, you will find that it gives you the what is that again? IUC name?
IUPAC.
IUPAC.
Yeah, IUPAC. Okay.
International Union of Pure and Applied Chemistry.
Yeah, like if I drag this over here.
So I'll read you what it says here. It said the default in organic chemistry, essentially the lack of any functional group, is given the term alkane, characterized by single bonds between carbon and carbon or between carbon and hydrogen.
Okay.
And then it gives examples of methane, CH4, and octane, C8H18. That's all they had to say.
Those would be alkanes. But if you broke one of those hydrogens off and you attached it to something else, it would be an alkyl group.
Alkyl group. Okay.
Yeah.
Thank you.
Yeah, with butyric acid, what you're seeing with the last carbon in that chain having a C double bond O and then an OH group is what's called a carboxylic acid.
Yeah. Yeah, you see my Wikipedia here? Basically, it always gives you the IUPAC name. So butyric acid. And then it gives you other names, which is pretty cool. And it gives you a nice little structure that you can look at, which is, you can't rotate that, can you? So anyway,
it's pretty close to what it looks like in 3 dimensions, though.
Yep.
3-dimensional structure.
That is something that has shocked me is how the names have evolved. And so the literature will have some of the older names, and sometimes they don't use the IUPAC name because it's so long. Yeah. Sometimes.
Yeah, like
lots
if
of common
try
names.
and give a name like the IUPAC name for like like mystric acid or something like that, it would take you forever. Because it's a very long molecule. It's like 12 or 14 carbons, like followed by carboxylic acid or something like that.
Yep.
And that's not even considering like terpene molecules and what they form. Like those are also, like in terms of IUPAC nomenclature, they're not hard to name, but they're just annoying. And so sometimes it's easier to call something by its common name.
Yep.
So that's historical.
Yeah, and the other thing about common names, they give you a bit of history. Like you can find out why they were named, you know, like butyric acid from butter. And acetic acid, I'm not sure where that got its name, but they all have like a history of some chemist in the 1800s. And it's good to read a little bit about that, and then you kind of connect things. So,
Yeah,
anyway,
by
that's
the way,
the
nice board. I like your board.
that's iPad. That's Linea Sketch. That's a product that my company sells, by the way. So everybody should go buy it.
Just give us the full sales pitch, why don't you?
I should. I should show you some of the drawings that people have done on this. They're beautiful. This is kind of like an artist sketch pad. I use it for this stuff, but anyway.
Well, so this is good free advertising for your product.
Yep. Yes. So then let's see here. We can get, and so basically we can also get these, which are, you know, the double bonds, and we can get triple bonds, and there's just all sorts of, you can see how the combinatorics explodes basically with all of this. And you might see damn, there's one thing I don't like about this is that put your hand down on it wrong, and I'm gonna have to complain. So there's a way to fix that. But anyway, you can see the combinatorics of all the different ways that you can hook carbon up because it has those 4 bonds. And you'll also see things like for ethane, you'll see something like CH3, what would that be? For ethane, you see CH3, CH3. Is that correct? Immutable? Why doesn't it look right to me?
Yeah, it is.
Right. It is. Okay, and then for propane, you'll see CH3, CH2,
Yep.
CH3. And then you'll see things like CH3, parentheses, CH2, 10.
Yeah, or something like that.
CH3. So that one has, that's dodecane, or, you know, it has basically 12 carbons in it. So you'll see those variations in structural formulas. But then when you get down to, you know, when you start branching these things and they become much more complicated, it becomes very difficult to, there are ways to write that, but with parentheses, but it gets a little squirrely after a while. So, but the important thing that I want you to know is that these are basic groups, you know, that you're gonna see everywhere, and you should commit them to memory and start working with them and consider them. And the other thing is the complexity that just absolutely explodes with carbon. I mean, carbon is an amazing little atom. Silicon doesn't do this so well. Do you know why, Immutable? Because it has that one extra shell.
Yeah, so there's a few reasons. One is that silicon has a D shell that allows it to form additional bonds more than carbon can.
Yep.
The other reason is, well, the 2 other reasons is that silicon is less electronegative than carbon is. So it's very, for lack of a better term, submissive with the types of bonds it forms. And the chemistry there is a little bit different.
Yep.
And the third reason it doesn't have the same kind of reactivity as carbon is that it's what we call oxophilic. So if there's an oxygen within the same compound, it will try to get a hold of it. Silicon and oxygen are very good at bonding with each other.
So I'm looking at the periodic table too. So silicon.
Okay, so it should be on the screen. You have it? So silicon is right under carbon, and then germanium, and then tin,
Oh.
lead. So I mean, these would have the same bonding, the same valence electrons, and you'll see pretty complicated silicates. And that's also something to consider when you're talking about geology. Silicates can get extremely complicated in the same manner, basically. You have carbon, silicon, and germanium. And nitrogen and phosphorus are together on one under another. Oxygen, sulfur, fluorine, chlorine. And neon and argon we don't care about because they don't do nothing. They don't like anybody. They're really antisocial. So.
Just a question then. So for the silicone, it'll try to fill up the 3p orbital. Is that what it would be? 3p, and then the D shell might actually get filled somehow instead of the 3p orbital.
Right. So what'll happen?
Orbital.
Right. So what'll happen is the 3p orbital will get filled, and then the 3d orbital will also, well, depending on what it's with, the 3d orbital might also try to be filled. So silicon can form 4 bonds in its principal valence shell. So for its p orbital, it can hybridize with one s electron and 3 p electrons. And then in terms of its d shell, if it wants to, it can form 2 more bonds.
Wow. Oh, that's right. I remember reading in Soderberg's book about phosphorus. They said the octet rule doesn't apply to phosphorus because of the d orbital. So I didn't realize, that's kind of the similar thing with silicon.
Yeah, molecules that have the d orbital available to them have slightly different reactivity because they can go a little bit beyond typical valence.
It's really informative. Thanks.
Yep.
Oh, let's see. I got some garbage up here. I thought I was erasing it. Nope, I guess I can erase that. Okay, so where are we going next? Let's see. So then you start looking at basically all the things that you can form with this. Like if you have a C, I don't know, is that coming through?
I can see it.
Okay, and then you can have an O in between the H. I'm going to go to a different color here, green. Do that one. So basically, you've got an alcohol, and I'm not drawing the hydrogens because they get just messy, and besides, I can't draw. So
would that be ethanol?
It would be ethanol. So that is the stuff that everybody's drinking in this country like it's water for some reason. A thing we worship. And methanol, you do not want to drink. Makes you blind. I wonder why it does. Do you know why it does, Immutable? Why does that make you blind? Well, ethanol has something, I mean, it really, for one thing, it's metabolized very strangely and very differently in different people. And it's burned differently. Some people can burn it like sugar and it becomes energy. Like for me, it's energy. And for other people, it really screws up your nervous system to the point where you cannot function. You cannot walk. Methanol is a little more aggressive, and I'm not sure why it makes you blind, but it does. So anyway, so then so that's an important group, the OH group. It's called the hydroxyl group.
Hydroxyl.
Yep.
That was the hydroxyl group and the carboxyl were the only groups I knew going through biochemistry.
Okay. Well, a pretty important one. So that's hydroxyl. So then if we take a carbon like this, and we have an alcohol, and we take 2 of those hydrogens out, and we create a double bond, then we have acetic acid or ethanoic acid, which is a carboxyl group. So that's your carboxyl. So that's pretty important.
So that's acetic acid?
Yep, vinegar. And if you remember, I said if you leave your wine, basically your wine barrel, my dad used to have barrels of grape wine, and one of them went to vinegar, and it produced a really good solid vinegar because it oxidized. So basically, the additional oxygen was added, and it kind of screws up your wine, but it makes good salad dressing. So, not too bad.
How did you learn all of these? Is it just by exposure that you begin to recognize the molecule and the name?
I think, like I say, I started out with Isaac Asimov's book, The World of Carbon, and then I went to The World of Nitrogen, and he managed to instill in me a love of looking it up and figuring out what it's related to, and that became really important in understanding organic compounds, is finding out that various things are related one to another. I'm trying to find.
Yeah, Michael, concerning your question about why methanol is so poisonous.
Yeah.
The reason for that, if I'm recalling correctly, is that methanol, when it goes through, when it's processed by the liver, it gets transformed into acetone, if I'm recalling right.
Acetone, really?
Yeah.
Into acetone?
If I'm recalling correctly.
Okay. Or is it formaldehyde?
Oh. Formaldehyde.
Because I know some people that have a sensitivity to alcohol, it converts it into acetone, ethanol.
Yeah. I think that's what they use in breathalyzer tests.
Okay.
Because they use, like, when you breathe into it, they're detecting like the presence of I believe it's the presence of acetone relative to ethanol.
Okay. Okay, let's see. Where should we go from here? So another thing you can do is, I want to do that there. Do that here. Get rid of the carboxyl.
So that's acetic acid. Acetic acid with the carboxyl.
Yep.
So would we still say that's a ethyl group with the carboxyl, or see, because that C is connected to the carboxyl group. So,
yep. So would
can
that
you actually
be,
overlap the carbon, share the carbon between the carboxyl group and the ethyl group?
Yeah. So another name for acetone is ethanoic acid. And the etha is part of the fact that the length of it is 2, so it gets the name, so it would get the name ethane originally. Since you have a carboxylic acid, you replace the ane part with oic, so you get ethanoic acid.
So if I were taking, like, if this were an exam question, they'll say identify the functional groups. I would identify the C and C as a ethyl group, or is that even correct?
You could identify this as the little carbon over there as being a methyl group.
Methyl group and then a carboxyl group.
Carboxyl group.
Yeah.
So
technically.
So
even though it can actually be modified from an ethane that became a ethanol that became a acetic acid, you can still call that a methyl group on the left.
Yeah, because it's a CH3.
I've never seen it talked about that way though, which is interesting. So
only in organic chemistry textbooks.
Yeah, I've seen an example.
In reality, if you use ethanoic acid, people are just going to look at you just like, why? Why are we doing that?
Yeah.
Like, we understand what it is.
Yeah, up here they notice they have a preferred IUPAC name of acetic acid.
Yeah.
Which is, yeah. And that stuff's kind of cool because what is this melting point? It's just it's a little below room temperature, right?
Yeah.
Or something? Yeah. So, I mean, it could be, like if you have pure acetic acid, I think it might be solid. It's waxy and solid at room temperature. And then you mix it with water and you get vinegar. You know, vinegar is what, 5%, I think, acetic acid. It can become quite a bit stronger. I think I saw that once. I saw pure acetic acid, which is kind of cool. So,
I
Anyway,
think it'll like melt your skin or some stuff like that. It's like
I think it
extreme.
would probably hurt you. I don't know. And if
Well,
you took a bath,
this is actually really informative. How we to be careful of the nomenclature that paper may be using, or a textbook, or
yep.
okay. So I would identify that as a methyl group, and then a carboxyl group, even though it's called ethanoic acid.
Yeah.
Okay, sure.
So, without getting into too much IUPAC nomenclature, because literally, like, there's textbooks that go just into that on how to do it.
Yep.
The most common idea when naming something is, number one, look at the longest possible chain of carbons that are in your molecule, and that's what becomes the parent name. And the other part of it is the suffix of the group is determined by, are there any functional groups? Are there any double bonds or triple bonds in the molecule? Is the group being represented as a ring, in which case you would have cyclo as part of its name.
That's where we'll go next, is rings. We'll go to rings next. But like right here we have, so the longest one is this chain right here. So it'd be 1, 2, 3, 4, 5. So it would be pentane. And then we have, so we'll have to pick a side. It doesn't matter what side we pick because that's right in the middle.
Yeah.
But if we had, let's see, hexane, basically, we would pick
You'd pick the left side.
Yeah, the left side. So this would be carbon atom 1. This would be carbon atom 2, and this would be 3. So that would be 3 ethyl pentane or hexane.
Yeah, 3-ethyl hexane.
3-ethyl hexane.
Is that because the ethyl group is attached to the third?
What did I
do?
do?
Yes, that's because in this case, the way we've chosen to number that branched alkane, the third carbon, the lowest numbered carbon has is the group that has the substituted alkane on it.
Yep.
So on the third carbon you have an ethyl group, whereas if you were to number it this way, it'd be 1, 2, 3, 4, and you're
You always go to the lowest. There's a certain order of groups that basically with that IUPAC numbering scheme, and you always try to work it out so that you use the lowest numbers. That sort of thing. Like if you see 5' and 3' DNA, basically that's what they're talking about, which carbon atom. And there's a numbering convention that we can get into at some later point here, and we actually show you nucleotides and riboses and things like that. So
yeah, with nitrogen heterocycles, they use a very particular numbering system. It could be historical significance, although I'd have to look more into why they chose that numbering convention, because I don't understand it personally.
Yeah, we might get ahead of that and look at it before we start talking about. But no, I just turned it into a 3-methyl hexane. So.
Yep.
So anyway, and so this would be 3-methyl that, and I'm going to go 3-methyl for 4-ethyl hexane. So anyway, is that confusing, Sal, or does that make good sense? So to be.
I can see it so far.
Okay, 3-methyl 4-ethyl.
And just out of curiosity, if you erase the
actually, I think I did it wrong, didn't I? You'd go 1, 2, 3 ethyl, or yeah. So it'd be 3-ethyl 4-methyl hexane. You could go either way. Depends on which way you decide to number these.
That's what I wanted to ask you.
Yeah. Okay. What is your take on that, Immutable? Which way? We'd want the ethyl first, right? So that would be 3-ethyl 4.
Hold on.
Is there a rule for that?
Let's see, which is the longest? 1, 2, 3, 6. So you'd have, in this case, it'd be, yeah, so one of the other rules with IUPAC is when you have two functional groups that you're trying to name, you try to name them by which order they appear alphabetically. So it would be,
That'd be ethyl methyl. So
yeah. So in this case, it'd be
3 ethyl, 4 methyl.
It'd be 3 ethyl, 4 methyl hexane, I believe.
Yeah, 4 methyl hexane. Okay.
Well, I saw Professor Dave have a whole thing on IUPAC, I think.
Oh, really? That would be worth watching.
I only looked it up because of his Cantoban debate. And I looked up his channel. I said, he has a lot of chemistry.
Oh, he has really great stuff. He has great content. He has a lot of views. So anyway, so we got a blank slate. So now there are, I wish you could draw two immutable on this. Well, you can. You've got your share, right?
Yeah.
We could get into rings.
Yeah.
So there's another thing that you can do that, you know, you're running along here, you've got a carbon like that, 5 of them, you could hook that one up to that one, basically. So now we've got a C, 2, 3, 4. So now we've got a, why am I blanking on cyclopentane?
Yeah.
Yeah, because there's 5 of them. So anyway, you can have rings too. So you can see now our complexity is exploding some more. So the possibility of forming rings between these different structures. And a really common one is going to be that you're going to see everywhere is, and I'm going to try to draw this well. I can just barely see my lines here.
Let's see, let me get my thing set up to.
So this would be hexane, or cyclic hexane. Cyclohexane? Cyclohexane. So, but then if we had double bonds between these and they were alternating, we would have benzene.
Benzene.
Yep. And what are some common benzene products? Benzoic acid. What is that used for?
I have no clue.
Benzoic acid. It's used for something. So it's always good to think about common names. I like it anyway. Freaky chemists like Immutable don't care, but I do. So.
But this would have a smell, wouldn't it? Isn't this what
yes.
they call aromatic? Aromatic
Yeah,
group?
benzene.
I'm sorry.
Benzene is fairly toxic.
Oh, the only reason I know aromatic groups is the 3 amino acids, tyrosine, phenylalanine, and tryptophan have the aromatic groups.
Yep.
That's the only reason I recognize it. I don't know nucleotides or sugars, but I'm a little more familiar with amino acids.
Let's see.
Can I share the screen? Can I share the screen?
Yeah, do I have to stop? I have to stop, right? Stop share? You go ahead.
I think multiple people can share their whiteboard at the same time. I'm not sure though.
Can you? On Zoom? Haven't tried.
I believe it's one of the sub options on share screen where the little arrow points up.
Yep.
Yep. I made you a co-host, so you should have all the screen. Yep.
Oh,
There it is.
so you can see it?
Yep.
I see a white blank screen.
Okay,
Nice.
unfortunately, you're on my little Mac window way the hell over here, because when Zoom first starts up, you have the opportunity to move it to another screen, but then when it fixes, you can't. So
I didn't know that. I mean, I can't do it on my Windows system. That'd be cool.
Yeah.
Let's see. So notably, like the first cyclic molecule you can have is this one. It's
Yep, and cyclopropane.
boy. Let's see.
What drawing programming are you using, Immutable?
I'm using, I have a Windows computer, so it comes with Microsoft Whiteboard.
I didn't know that. Do you like it?
Yeah, it's pretty good.
Okay.
I'm reading about cyclopropane. And why it's not a good idea. Extreme reactivity. If you
Yes.
mix oxygen with it, it will explode.
Yeah, so the reason for that is quite simple. Well, at least to me it is. If I draw it again, a little bit more accurately, let's see. What's that? Oh, that lets me draw a little diamond, but I don't want to do that. Let's see. Let me draw. Yeah. Let me draw 1, 2, 3. Yep. So the reason for that is the bond angle between, so the angle between all of these carbons has to be a very particular value. Particularly, triangles always sum up to 180 degrees. So each of these angles has to be identical to each other. But unfortunately, what that means is that the hydrogens, which are part of this molecule, are very crammed because of the way this triangle is locked into place. These hydrogens really don't have too much don't really have a lot of space to move around. And so that's why it's very reactive. There's a lot of what's called steric hindrance between these hydrogens. And the reason for that is technically a carbon-hydrogen bond is the same thing as, well, oh boy.
I'm trying to make cyclopropane with my molecule kit. Not working.
Yeah,
Breaks up.
You mean that's how tight the angles are?
Yeah.
Yeah.
It just doesn't behave well.
Is a carbon-hydrogen bond, from the perspective of quantum mechanics, is the same thing as drawing this type of thing. So it's the same as drawing this kind of lobe of electron density where electrons are being shared between carbon and hydrogen. And in this case, there's just a lot of overlap between these orbitals, which isn't good.
So how about cyclobutane?
Cyclobutane is a little bit better.
You don't see it very often.
No, you don't, for a similar reason. But actually, this lets me get into a point that I want to get into about aromaticity and cyclic groups. But so cyclobutane has this kind of shape. It has 2, 3, 4. Yep, there we go. And so this is cyclobutane.
Butane.
Yep. And each of these are right angles. So it's a little more stable, but not significantly. And for the same reason, the bonds are still a little too close together for it to be happy where it is. Although, that being said, to introduce the concept of aromaticity, let's do that. It would be, yeah, I would need to introduce a double bond here. And you would need to have a positive charge.
So it says that cyclobutane is of no commercial or biological significance.
Yeah, it rarely forms.
I would hate to be that molecule.
Yeah, it has a pretty interesting existence.
That would be like the atheist version of molecules. It would be meaningless.
Oh God,
I had to put that in there.
I know. You got to put it in our place.
Well, we could describe it as like pure mathematics. You know, it has the mathematicians be offended if it had some utility.
Yes. Interesting. And I can actually make that with my molecule kit because it doesn't strain as far as cyclopropane, which is interesting because the plastic molecule kit kind of mirrors what happens at the atomic level.
So the angles are kind of fixed in the molecule kit, but that's not always that may not actually represent what always happens.
You can bend them a little bit, basically,
Okay.
but they have a natural tetrahedral form that they want to be in. And
can I grab my kit?
Sure.
Go ahead.
I'm so excited! I got one.
So you want to go to aromaticity?
Yep. If you can see my screen, this actually is an aromatic compound.
Really?
Yes.
With just one double bond? Really?
Mm-hmm.
What is that called?
Aromatic
Aromatic butane.
Let's see. What is that called? What is the name of that molecule?
I'm going to try to find it.
Cyclo.
N-butane? Yeah, they use the N form of it. Is it called N-butane?
Yes, N-butane or N-cyclobutane.
So butane and N-butane, they don't, aromatic hydrocarbon, Wikipedia, so they, heteroarenes. Well, we won't go there yet.
Not this one. Let's see.
What if there's an N-pentane?
No, not that one. It could be this one isn't, but should be. Cyclobutene.
Get no love for N-pentane.
So, why do they call it? Is every cyclical carbon are those always aromatic, or is it just a certain number of carbons that constitute aromatic?
No. So here, let me give the reason. Let me show a molecule that's aromatic. This one has a very complicated name, and so I'll use a simpler one.
Aromatic refers to aroma, so that's a clue.
Actually, an even more constrained molecule that has aromaticity is this. We've seen it before. So
Aromaticity.
is this? This is a double bond, and you have plus charge. And that is aromatic.
That is?
That is indeed.
So that is N, what was that? N-cycloprotein or propane?
I think it's called
N-propane? What does it smell like?
Probably doesn't smell that bad. Probably doesn't smell very good.
I know it puts you to sleep.
Since it has a double bond, how come it's not called a propene?
It is.
Oh, okay.
Cyclic propene
Propene.
could be. That's where names get all confusing.
Propene.
See, that's my 240-piece molecular model kit.
Let's
So you
see.
can hear me pouring out all the little marbles.
240 pieces. Where did you get that?
Atomic Architect for $21.
Atomic Architect.
I didn't know what I was buying. I mean, I don't have that. I have 86 atoms, 153 links, and 1 tool.
Right. So this is a. Oh God.
Can I? Atomic Architect. Somebody's talking. Oh, there it is. Atomic Architect. 267. I can't believe that. I got to buy that.
Yeah. So this molecule is kind of an exception to the rule with aromatic compounds. So the first rule of aromaticity, or the first of 3 criteria for it, is that a molecule must be cyclic. Must be cyclic. Molecule must be planar.
Mike, I got a question.
Yep.
How do I do a double bond with a carbon in your molecular?
That I don't know with that kit. There should be some sort of a double bonding mechanism there. I'm looking at the kit now, or trying to find information on the kit, and they only show the hydrogens hooked up to it. I have one that has, if I can show you after we get back to the camera, but I have one where you can actually hook the bond. You can bend the bonds a little bit so that you could form double bonds. But forming triple bonds, I have never tried with this thing.
Now I have these things that are shorter than the long ones. Is the double bond, would that make the carbon atoms closer together?
I believe it would, but not a lot.
Okay.
Yeah, they are shorter, yeah. And I think triples are even shorter, yeah. Mutable question. Mutable's working on his 3 rules. Molecule must be cyclic. Molecule must be planar with conjugated pi bonds.
Molecule must have 4n plus 2.
I am going to try to find that on Amazon. It's one kit I don't have. I have a kit with about probably 5,000 pieces, maybe 10.
Wow.
That I keep in a drawer. My son's got it for me for Christmas. And it's a little bit different. They're a little more flexible, but they're not as pretty. They don't give you that pretty atom field. Four n plus 2.
I can't even make a triangle with this kit. Or unless I did it funny.
All right, those are the 3 rules for aromatic compounds.
You must have 4n plus 2 pi electrons. Oh, nice.
Must have 4. Unfortunately, I don't know what those are.
4n plus 2.
What pi bonds are.
Oh, okay.
Is that general chemistry? It's been like 30 years.
No, it's basic organic chemistry, but that's okay. So, can I get a little bit of minimization here? I just need. What the hell?
I don't know how to make a triangle with these 3 carbons.
Those look pretty rigid. Advanced molecular models. Here is.
Maybe I'll
Design
do
your
better
own.
with a cyclo. Maybe I can make a pentane.
And let's see, the pi electron essentially is the most basic type, or the most basic example is of ethene. So pi bond, pi bond, pi bond has one pair of one pair of sigma electrons, and one pair of pi electrons.
Just a question: Are sigma then and pi, are those like hybrid orbitals? Is that what it?
Yep.
Or
Yes.
okay, that's where I'm gonna have trouble. I do remember hearing the term, and I really struggled with that. I mean, I don't want to bog us down. I mean,
Yeah.
if that's something that you think I should study later, I'm happy to do that.
No, I mean, if it's a fairly quick, fairly simple concept, especially for people who have some familiarity with quantum mechanics. So the
Yes.
basic idea is that in chemistry, at least, we don't describe the positions of electrons. We describe their probability
Okay.
of occurring, or a probability of being somewhere around the nucleus. And mathematically, a wave function, the general wave function psi for 1s electron has the most basic kind of shape that it can.
Sphere. Yeah.
Well,
That's ironically what I
yeah,
studied. Like 25% of my quantum class was on solutions, 3D solutions to the Schrodinger equation, and they use these spherical harmonic solutions. So
right. Yeah, you use that. I also studied that a little bit. They're comprised by taking a few quantum numbers and solving a few subcases of the Schrodinger equation.
oh, yeah, see, this is my quantum book.
Oh, I used the third edition of that book, actually.
Okay,
Nice.
so we're on the same page.
Yeah, I'm still a little lost with that book.
Well, it didn't treat the bras and Ket's the bra and Ket notation real well, and so that was its main deficiency. But it was a good introductory book. So
it's fairly rigorous with the proofs that it gives. The mathematics part isn't very hard. The only thing I struggled with a little bit was they introduce operations that require you to know Fourier transforms. But unfortunately, I never learned that. So
yeah, they're long and tedious.
yeah.
So yeah, see, this is from that's how they did the solutions to the orbitals for the very simple ones.
Yeah.
Spherical harmonic.
Who was the author of that book, and what's the name of it again?
David Griffiths, Introduction to Quantum Mechanics.
Maybe Griffiths.
So you'll actually get to see how, oh yeah, see, they took Schrodinger's equations and you could see let me see if I could, you could see the shapes of the orbits. It's really nice because you could do this from first principles of Schrodinger's equation, and it will predict the shape of the orbitals for, I guess, just that atom, an isolated atom. So if I understand this correctly, once you involve another atom, the solution to Schrodinger's equation isn't quite so tidy.
No, and the reason for that is, well, one of the main reasons is that, well, quantum mechanics itself isn't a relativistic theory. It considers the velocity of electrons to be very low. But more importantly, at least the way I conceptualize it, is electrons from classical physics have a negative charge to them, and that makes sense. Although that kind of becomes problematic in the case of multi-electrons, because if you're trying to describe where an electron is in space, well, clearly there's going to be some dependence on how many electrons there are in a system, because electrons have an electric field, and if they get too close to each other, that electric field will cause them to be repelled. So you're modeling the general equation of the Schrodinger equation for two electrons, but also having to account for some repulsion between the two electrons that might occur. But I believe in Griffiths' book, they actually go a little bit further. They go into a little bit more advanced quantum mechanics. So they get into perturbation theory.
Yeah.
So corrections to the wave function when you start including like two electron systems or things like that.
Oh, I just wanted to, my understanding is that the Schrodinger equation is for, like you said, low velocity electrons, but they do model the relativistic, it's called relativistic quantum mechanics, relativistic quantum chemistry, because like the uranic and transuranic elements, you need relativity, special relativity, not general, to be able to explain.
There are things that happen.
Yeah. Yeah. Now there's one other subtlety there. It's not that important. Yeah. So Schrodinger is kind of like a Newtonian-ish quantum mechanics. The Klein-Gordon field equations deal with the ones with special relativity. Oh, now I know what I wanted to say. The Pauli exclusion principle actually comes from joining quantum mechanics and special relativity. Not a lot of people know that. When I heard that in class, that just blew me away. The professor said it's very hard, we're not going to cover it. But I thought that was interesting. The Pauli exclusion principle is tied to special relativity.
It's kind of interesting.
Isn't that cool?
It is.
Okay, so let's see. Proceeding with aromatics and not getting too hung up in pi bonding.
I know. So, yeah.
Sorry about that, Mike.
Well, that's all right. Immutable's been like a harsh taskmaster schooling me on relearning organic chemistry and orbitals and what else?
We haven't even gotten into like constitutional isomers yet. God.
Oh well, yeah, those are pretty simple. Constitutional isomers is a new term that I did not have when I was a child. Basically, that's really, at least nobody used it in the textbooks that I was looking at back then. So
why did they have to add the word constitutional? Does it? Isn't an isomer or?
Well, there's stereoisomers and there's constitutional isomers.
Okay.
It comes about from the fact that if I give you a general formula for a molecule, so if I give you something like, I don't even know if this is correct, but let's see.
I have a chat. That's the next section is constitutional isomers.
Yeah, that's what I would show. basically showing you different ways to hook the carbon chain up.
Yeah, so if they gave you something like this, which it might not even be proper.
C8, C13.
So the cyclical ones then wouldn't those be constitutional isomers? So
They
the
are.
okay.
So for instance,
So your propane so your pentane can be linear or cyclic, and those would be constitutional isomers. That be correct?
I believe so. Actually, let me check.
It would have a different number of hydrogens because one of the carbons would be hooked back. So I think it would have a slightly different formula.
Yeah, I'm thinking that's correct. Yeah, I'm thinking so. Yeah.
But the different ways that you can complexify alkanes, you know, that I was showing you earlier, with, you know, hooking things up in the middle and all the branch chains and all that. The things that make your car knock rather than octane, you know, which makes your car run way smooth. So
yes.
Yeah.
Yes. See, like, it's just like what you said, Mike, is it has to have the same molecular formula.
Yeah.
So the cyclic one and the linear would not have the same molecular formula.
Yeah, but I'm not
So
sure
they're not
if,
constitutional isomers.
I'm not sure if I'm right about that.
Do you want me to read you what the book said? Now that we have reviewed how to draw Lewis structures and learned the line structure shortcut, it is a good time to learn about the concept of constitutional isomers. Imagine if you're asked to draw a structure for a compound with the molecular formula C4H10. And then they show the two ways you could draw it. So compounds that have the same molecular formula but different connectivity are called constitutional isomers. Sometimes the term structural isomer is used. So that's all they had on it. That's page 20 in the book.
Yeah, they're the same. In fact, before you said that C4H10, I was using that as an example to refresh my memory. But yeah, so a constitutional isomer would be its constitution has changed, but I don't think its formula has. So
okay. So are stereoisomers then a subset of constitutional isomers? Would that be correct?
what would you
So
say that?
the left amino acid and the right, the D amino acids would be constitutional isomers.
Immutable? You want to weigh in on that one? I'm not sure if that's even the right way to think about it.
Let me think.
If constitutional isomers, one class, and stereoisomers, that's when things, you know, things have a right and a left characteristic to them. Like the mirror image is, you know, going to be different than the actual image.
Right. So stereoisomers concern, they primarily concern chirality. So chirality is actually something we should dive into another lecture.
Another day. Okay.
Yeah, I think we want to proceed and look at benzene and talk about conjugation a little bit.
Okay. So benzene is 5 or 6?
6.
6. Okay.
Cyclohexane with 3 double bonds.
So I just learned something about my molecular set.
Yep.
I might have to put a piece of tape to indicate a double bond.
Yeah.
Because they don't have any particular link that makes
they
it
don't.
double. Okay.
Yep, this is benzene. And it meets the goal for, it meets the criteria for aromaticity because it has 3 pi bonds. Well, 6 pi bonds, 6 pi electrons actually. Because each pi bond has 2 pi electrons, so it would be, this would satisfy the case for n equals 1 in this case. If you check it, because total, there's 6 pi electrons here, so there's 2 here, there's 2 here, and there's 2 there. And so that'd be 4n, 4 times 1 plus 2. So for Huckel's rule, it's the n equals 1 case. And actually, those 3 rules I wrote down earlier are called Huckel's rules for aromaticity. And if you consider the formula for 4n plus 2, if you consider a simple table, so for values of n and 4n plus 2, it actually tells you how many electrons you'll need in order to, or pi electrons you'll need to have an aromatic compound. So for n equals 1, 4n plus 2, 6. For n equals 2, it's 10. For n equals 3, turns out to be 16, and so on.
And n is the number of?
And n is the, and n essentially is the number of pi bonds, essentially, in a molecule.
And then so 4n plus 2 means?
This represents the number of total pi electrons.
Okay. So we just have 1 pi electron in benzene?
You have 6. So each pi bond has two pi electrons in it. I'm trying to figure out a way to explain that that's cogent.
I'm willing to review it on my own. I don't want to hold up
Yeah.
the discussion.
No, it's fine. It's just that there's 2 pi electrons within a pi bond is the important aspect here. And essentially, so when you see 3 pi bonds for the molecule, you can say, oh, well, that should be, I'm confusing myself. Gosh, at least, let's see, 2, 4, 6.
That's what I hate about trying to teach somebody stuff.
I know.
I was confused myself.
Right. So if this is 6 pi electrons, right? So these pi bonds each have 2 pi electrons. So 2, 4, 6. Okay. Are they conjugated? Yes, they're separated.
No, go.
And okay. So there's 6 of them. So that satisfies the case for n equals 1. And if you were to draw others, you would find other structures, other pi electrons for, you'd find other possibilities for how to create aromatic compounds. So one of the important aspects is that this rule for n, it must hold for n equals integers. So it has to hold for n equals 1, 2, 3, 4, blah, 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 blah. And that's how the number of pi electrons is determined. And if you were to consider this, and for the number of pi bonds actually that need to be formed, all you would do is you would say, if you were to give this a name, say, say a name K, for instance, I don't really care what it's called. Then K over 2 tells you how many pi bonds should constitute an aromatic compound. So This would be 3. This would be 5. This would be 8. And so on. And as proof of concept, the next very benzene-looking molecule that shows up a little bit in chemistry is this compound, which I'll draw. So it has yeah. So I believe it's going to be I believe that should be should be fine. It's this compound.
What do we got here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5.
Yep.
Oh,
5.
is that anthracene or something like that?
I believe that's what it's called. Hold on a sec. I need to take a call.
Naphthalene.
Yeah.
Okay. Let's see.
Naphthalene. And I think that, you know, it's interesting because you're covering, this is a different look at the stuff in my book. So it's a good review. Naphthalene. So let's see what page they have naphthalene on. Naphthalene.
Love you. Bye. All right, guys, this has been fun, but I got to get going, unfortunately.
Oh, well, thanks for your time.
Yep.
Very well. We'll do it again if you have time. So thank you.
Yep. Nice being here. I'll be sure to see you around or hang out if we get some free time.
Yeah.
All right. Well, take care.
Take care. Well, Speed of Sound, it's you and me. Could I show you some of my homework stuff? I wanted to ask you, I had some questions, just maybe just trivial questions. Do you see my screen? Oh. Oh, mic's muted.
It's a good thing I was muted
Oh, okay.
because I swore.
I had just some
This
homework
convenient.
questions.
Okay.
What,
We're
what
looking
is
at
this? What does
formal
this symbol
charges?
mean? I'm sorry.
Okay.
What does this symbol mean here on the
Is-
bromine? Why does it have that kind of like sort of triangle? I can kind of understand what the line means. I've never seen that. It didn't explain it in Soderberg's book.
Okay, I'm guessing that those would be 2 carbon atoms. And that would be a, I could look it up here and see if I can figure it out. So that would be, got a cyclic bromine. Interesting.
We could save that for
Yeah,
another day.
we probably should.
I've just never seen that notation.
Okay.
And so I got my formal charges wrong, and I had to, so when I did my homework, I got some of them correct.
Yep.
And then I totally blew some of the other ones.
And that is the stuff that I'm reviewing right now with Immutable, is basically learning how to do formal charges. When I taught myself most of this stuff, I blew by a whole lot of things because I didn't find it necessary to go where I wanted to go. And that was one of the skills that I didn't develop, and now I have to develop it. So he's basically, I think sometimes he's frustrated with me because because I don't I don't learn things in a linear fashion at all. He keeps telling me I got to read the black part on the page and not the, ignore the white part.
So since you said you're interested in phosphate chemistry, that's the
Yep.
one that is interesting, and it has these formal charges. But then I'll show you some of the stuff I did. This one wasn't too bad, where I couldn't tell it had any formal charges.
Yep.
What they said is try to build a molecule. They gave me a formula and I had to build it. Sorry.
Okay.
So I built a molecule like that. So that's the 5 carbon, that'd be like a pentane with a oxygen.
That would be like that would be an aldehyde with a double bonded oxygen, that is.
Yeah. See, I don't know
Okay.
that I got my accounting correct, but this was, some of the formulas were not too bad, but then I really blew it with some of them. I had a hard time building this one.
Okay.
And so they said, well, he didn't provide any answers because there could be so many different isomers.
Yep.
So he didn't even, I just guessed. So there's not any, but this one, I'll show you the one with the nitrogen just killed me. That took me 2 hours, and I still took a while for me to get the something that would even work. I'm not even sure it's a valid molecule, but
So yeah, I don't even know what that is. That would be a nitroxide, I think, or something.
yeah. So I had to go, I had to go into the book, and I said, okay, I just kind of go by the connections now.
Yep.
Like if I have the oxygen and I have 3 lone pairs, I'll just say it has a negative charge.
Yep.
It's kind of hard to do the accounting in my head. And then, this one was a disaster. I had such a hard time putting C4H3O2 minus. I had to pay attention to the, if it's an ion, and that took me about 45 minutes to kind of come up with a solution like that.
Okay. So that would be like an acetate or a carboxylate, basically, with a negative charge on. You got an O2, and there's going to be like an OH group, and there's going to be a double bonded oxygen, and you remove the hydrogen, and you'll end up with a negative. So you'll end up with a carboxylate. That would be an ionized carboxylic acid, basically. The hydrogen would go away. But yeah, formal charges are something you and I should both be practicing.
Yeah. And by the way, these are made up molecules by me. I didn't, they could be totally illegitimate. So don't take this one too seriously.
Yeah,
I was just trying to get build something that had the same.
Well, that one would work, I think, except, let's see, you got 4 there, you got 4 there. So yeah, that would work. So that would be that'd be a combination of a carboxylic acid and an aldehyde. So that would be, let's say, it'd be so it'd be butanoic acid. So that would be 1, 2, 3, 4 aldol butanoic acid, I think. And I think it's aldol. Not sure exactly how to name that one, but yeah, so that one's legitimate. That looks good.
And then let's see, I had another, and I was just finishing up from where we left off, and it was really good discussion that we had. See, now I can, So we talked about, we talked about the formaldehyde. So I'll try to remember how to recognize this. So what would we call this group? Is that a group here if you have a carbon and 2 hydrogens?
And 2
That's not
hydrogens.
really a group. We'll just call it formaldehyde, the whole thing.
Where is, I'm not sure what I'm looking at. Are you pointing at something on the screen, or let's see.
This
Carbon.
molecule here. So you can see this, the line structure here. Yeah. What would we call this? The whole molecule is called a formaldehyde.
It is? Yeah, we're looking at the one with 4 carbons, or has my screen share stopped sharing?
Oh,
So-
wait, I screwed up.
Okay.
I totally screwed up here. Hang on.
I don't think
Sorry
we're on
about
the-
that.
I don't think we're on the same
I
page.
must have.
Okay.
Oh, I know what I did. Hang on. I totally messed up. And I'm almost done. I don't want to take up too much of your time.
Yeah, tonight, 4 of us are going to be chopping you and some other people from Standard for Truth channel up on my channel, Speed of Sound of Gravity. We're going to be looking at some videos, not so much you, but some of the other individuals over there.
Oh, that's
going
what
to
you
be-
meant by chop chop.
Chop, chop. We're going to be doing a little critique.
Okay.
And yeah,
We'll exercise 1.
all friendly sometimes. So, okay, so formaldehyde.
Oh,
okay.
does that have the formaldehyde there?
Yes.
Oh, okay.
Or wait a minute, hang on a second. But before I confuse myself, let me make sure that I'm on the right page here. Yes, yeah, it's formaldehyde.
So this is when I emailed you. I said that's where we were having problem with the molecular formula. Like I was complaining
yes,
that
okay, I
I
remember.
said I didn't like the way that the professor, he said HCOH because that's kind of deceptive, because I saw other ones that gave him, like H2CO or something that seemed a little more.
Right.
And
Yeah, because HCOH would imply that there was a hydroxyl group to me,
hydroxyl group.
and that wouldn't be right. Could I share my screen real fast,
Yes.
just before we're done here?
Yeah.
Let's see, I will try that. And share screen and go share. So am I sharing?
Yeah, I see it, and it says our rules for, your rules for, 4 rules for aromaticity.
Oh, what? Okay, yes. Okay, this is just a bunch of Google images. And Immutable was trying to show you one down here. I think it was, what did we decide it was?
Naphthalene?
It was naphthalene. Yeah, naphthalene right there. Can you see my mouse move over that?
Yep. Mm-hmm.
Because that's naphthalene. There's toluene. You notice we have a methyl group on top of an aryl group. So this is your aryl, that's your methyl. And here's benzene and naphthalene. And then there's pyrenes. Chrysene, I'm guessing that would be what makes chrysanthemums smell good. Phenanthrene, which you can say, what I want you to see is the complexity that can arise from all of these different aromatic configurations. Naphthalene, here's pyridine. You put an N instead of a carbon. And furan has an O instead of a carbon. Indole, which is, indole, I think it's a dye. I believe it's highly purple. It has a 5-carbon ring attached to a 6-carbon ring. And you could just look at these forever. And there are billions of these compounds. And the plant world is extremely rich with them. They're all over the place, and they have a lot of physiological properties along with phenotypical properties for the plants, like the colors of flowers and things like that. Like anthracene, I believe, is what makes, and I could be wrong about this, but I believe it's what makes your leaves turn colors in fall. And
So just a change in the position of the double bond will change the.
yeah, it would change the behavior. But these like anthracene here and benzene and toluene. These are all conjugated, so those double bonds are not fixed. Those actually float around. They become a hybrid of their own, and this becomes sort of so every carbon has the same characteristics, and that's kind of where we were going before Immutable left.
Oh, is that what they mean by resonance structure, or is that related? Okay.
Yes, that is resonance.
Okay, so I was trying to take the MIT courses or some of these free online, where they just record the lecture.
Yep.
And that's when I got blown away. And that's why I like Soderberg's book. He didn't go into that real fast.
Yep.
Just kind of, he didn't start with it. He started with stuff that I could digest without a lot of Gen Chem.
Yeah. Yeah, and there's, I don't know, it's, I think looking around at the different compounds and getting used to them is going to be more valuable than unless you want to become an organic chemist.
No.
And
no,
you actually want to go into, unless you want to become a Walter White, if that's in your career.
Who is he? I'm sorry I don't mean to insult anyone. I actually don't know who he is.
Oh, you haven't watched Breaking Bad?
No.
Breaking Bad was where is this a family show? Should we talk about it?
Yeah, it's a family show. Okay, so we won't go there.
Okay, I'll tell you after about
right.
Breaking Bad, Walter White, and the character arc. Wonderful character arc because one person starts out really good and civil, and the other person starts out pretty evil, and then they switch positions in the middle of the series, and you can see the transformation as the bad person becomes so upset with the good person turning bad that he actually becomes a better person. But it's an interesting series. So
interesting.
Yeah, we'll tell you more about it later. But let's see, what else did I want to show you?
Well, I'll stop sharing my screen. I just wanted to say, when they give me these formulas and I have to reconstruct.
So they give you the four things at the top.
Oh.
And that's in Soderberg. That's the name of the chemistry text.
Yeah, Soderberg. Just the first 20 pages are really good. It's the free online organic chemistry text, which is nice.
That's the one you gave me. Okay.
Yeah.
I've got a couple behind me. I've got Lewis, and I've got Morris, and I've got what is the other one? McMurray, and then I got Bordwell. Everyone has a different flavor, and then there's Klein, which is the one that Immutable is going through with me, and I'm a little upset with it because for the first 5 chapters they talk about formal charges and ions and stuff, and they don't talk about anything real. And relating this to something real is kind of important. So,
well, I know what you mean, because when I was studying, it's like I could see Immutable Destiny liking the quantum mechanics stuff.
Yes,
that's really theoretical. And what was really funny was it was like 20% through the course we finally got to the hydrogen atom.
Yes, yeah. And then for anything more complicated, they have to fudge. Because the equations are far too complicated. So.
I had someone loaned me a copy of Klein's book. He taught at Johns Hopkins, so that's why, it's like that's my alma mater. So I sort of like him.
Yep.
But I appreciate hanging out with you because of your love of this stuff. It's infectious. I don't know that I'd start studying organic chemistry if we didn't bump into each other. Because I've been meaning to, but it's since you have such a love for it, I said, this is so cool. So,
when the neat thing is that when you start looking at this, you can go on the wiki. Am I still sharing my screen?
Yeah. Mm-hmm.
Okay.
There's the formaldehyde.
So you can go on the wiki and you can look up like butyric acid and you start reading about it, or you can look up, let's see, aromatic, whatever. Aromaticity. Here's where we get to the orbitals, that sort of thing. And they don't have, but you can look up anthracene, and you start looking up compounds, and you find, oh, DDX11. How about that? Let's see, you look up like anthracene, and I encourage you to do this.
Okay.
Because it will widen your knowledge, and it will always be useful to you in biology. I mean, you'll always find things that are connected to this. Red dye alizarin is anthracene, basically. That's the three bonds. And they show you photodimerizes. That's interesting. But you could just go on forever and just read about these things. And they're very beautiful. And you'll find, that, I mean, suddenly something will pop up and it's like, oh, that's why roses smell the way they do. Or that's why roses are the color they are. And you'll find all these different compounds. It helps to Google them, look at the images, and start to get used to compounds. And the thing I wanted you to take away from today was basically, so we got the alkyl groups, we got those down. C, the CC, whatever. The fact that you can grow the complexity by branching these things in many different ways. They could go like that, and there's that complexity, and then the fact that you can have rings, okay? And the most important rings, it seems, in nature are these conjugated rings. These become very, very important. They're aromatic. You can basically disappear one of these and put a nitrogen in, and we're going to end up with purines and pyrimidines and all of that. And those, of course, go into nucleic acids, and it just goes from there. So the more you get familiar with different common compounds and play around with that, number one, chemistry will not be boring to you. And number two, you will get a really good background for biochemistry. When you start looking at the formulas and stuff, you'll say, ah, that looks like this. Therefore, there might be a connection, that sort of thing.
Just a question. What does conjugated mean? Is that double bond? Is that what conjugation means?
Yeah, this is the conjugate right here.
Okay.
Basically,
all right.
yeah. Well, a conjugated compound like if you look at vitamin A, you'll see this every other. I believe every other is conjugated. Okay. And this would be resonance, because these move around. But these conjugated.
That's really cool.
Yeah.
That it would be resonant.
Yeah, and it ends up planar. They end up becoming a plane. So they're like in a plane. They're like that. And so anyway, okay, so I wanted to show you that. And I want you to just sit around and draw some of these and think of your own molecules. And there are some interesting things like peroxides, which basically look like that. I think, I'm not sure which peroxide that is. That is a very reactive compound. That's an oxygen right here. So, but the ring is highly strained, so it's extremely reactive. And okay, that's about it. So look around and see what you got, and I'll stop sharing here, and I want to show you something. And there is a wonderful book here. I'm getting my World of Carbon back, but this is by Isaac Asimov. It was written in, I think, like when I was like a real young teen, very, very early. But he gets into things like he'll tell you why fish smell, why rotten fish smells, and he gets into just all sorts of really interesting compounds and tells you about them. Dyes. This one is aniline, the one that he's showing right there. And these little books give you organic chemistry in a much richer sense than you're going to get it from plowing your way through those first 4 or 5 chapters. And if you get anything from talking to me in these courses, you will get a love for the complexity of these compounds. So, and then
yeah.
I drew a butane. So
Butane.
I have molecules here, and it's kind of strained.
Yeah, I can't do much smaller than the hexane. They put it.
I have
Oh, I wanted to say that the textbook,
thousands of these.
Soderberg, he
Yep.
said the difference between his textbook and others is the other organic chemistry courses are written like they're to train organic chemists, not
Okay.
not biology types. He said he focuses so much on biology, so maybe it's
Which is
been a
good.
much nicer read.
Yeah.
Uh,
Yeah, that's good.
I think I'd probably suffer through Klein's book.
Yep.
So, hey, Mike. Well, we can do it again, and thanks for the encouragement. And you've really helped inspire me to study this stuff, and it's
Yep.
actually been fulfilling because now I'm looking back at all my biochemistry stuff,
Yeah.
and it's starting to the dots are connected. I mean, I really was going with the seat of my pants because I didn't have even really basic organic. So
And I think the next place we can go is sugars, carbohydrates. And we can start taking a look at how those are structured. And then you got the ribose part, right? And then so you got another piece of DNA. And then we can look at ring structures for purines and pyrimidines. And then you got the other part of the nucleic acid or the DNA. And from there, maybe the next time we can look at amino acids and all of that. And I'm trying to increase my own knowledge at the same time so that I'm not a bad teacher. So
well, as long as it's benefit to you as well, then I'm thrilled.
it is.